Good afternoon, we are Christopher and me, Fernando. We're going to explain our project based on Counter PCD mod 50K. We have here 3 inputs and 6 outputs, corresponds to the numbers, the terminal count, and continuable create direct and our clock. Our aim here is to design this chip with based on the plan C2. We're going to use our universal component Counter mod 16. As we will see later, we will use the truncation technique, and the chip we are going to use is the cyclone 4. As you can see here, we have different states, and all these states are coded in binary. So it starts with all the outputs on 0 until our last number, that would be the 49 999. So this will be our last number, and as we can see in our function table, we see that when count enable is equal to 0, stop counting, and when count enable is equal to 1, when the rising edge happens, the counting will be adding. So adding one unit, I mean. So it's easy explaining here in this piece of code that TC50K will be equal to 1. It means that when the counting finish, or finish, I mean achieve the last number, when counting will equal to 1, and we have our last number that it's equivalent to 49999. Our last number is here. In this timing diagram, we can see that as previous explained how this counting happens, and maybe here the most relevant is when continuable goes to 0, the number that is the the state keeps happening here until 2, and will only add 1 unit when the next rising edge and the continuable equal to 1. So here this is a resume timing diagram, because will be pretty large until imagine counting until 49, 99, 99, so will be a pretty large timing diagram. Here we have a state diagram. As previous explained, this continuable and the rising edge happens, will be changing or state, and we can see here our output coded in decimal. So this is our second number, that would be 1, the previous one would be 0, and the last one would be 49,999, 49,998. So here we can see that our chip and how it is implemented. So we can see here that we can differentiate between inputs and outputs and signals with this color. Maybe here we cannot appreciate it because they have different colors. So as the black one are the signals. In this case, as I said before, we're using the truncate technique in order to build the counter BCD 1 digit, but we can see previously with the counter mod 16 used in this box, that is the chip 5. So how we truncate this? We will be counting until 4. That 4 happens here. This counter mod 16 will be counting from 0, 1, 2, 3, but when it happens to 4, 4 would be 0, 1, 0, 0. So if we negate 0, we have 1, 1, 1, and 1. All this happens to be 1, so it happens to be load equal to 1. So as we are using the load, data in will be equal to 0, and as the data in is equal to 0, it will be counting from 0 until happens to 4. So here is a clear example of how the truncate technique works. And another thing that would be remarkable here is that our continuable happens to be 1 when the previous chip ends the counting. So this is how the counting works. So for instance, if we are going to count the tens, tens will only increase when the units finish. So this is a basic idea of how this chip will work. So as I said before, in our annex we are going to work with the counter BCD one digit that this chip is used to build or counter BCD 50K mod 50K. We are going to explain this one. So we used it with the plan C2 and our component counter mod 16. This is how it's going to happen. So we can see, well, latches here. So when this racing edge doesn't, this glitch doesn't make stop this counting, but here it happens, so it keeps the number 3 and 3. So we can see here that the terminal count is sensitive to the counting or to the counting able. As we can see here, we can see that how another way to use the truncate technique. So we happens to be counting from 0 to 16 with a counter mode 16, but instead to going from 9 to 10, we change, we go directly from state 9 to state 0. So in this way we obtain a counter mode one BCD one digit. So Christopher.
Now I'm going to explain how we develop and test the counter PCD mod 15,000. So for that we do this BSTL file using the planning and creating all the components of the counter mod PCD 15,000 using the plan. So having this file, we are going to Quartus Prime and using the Cyclone 4 chip target, we get the RTL viewer that here we have the schematic, and we can see that the counter PCD one digit is created with the counter mod 16. And the next step is view the technology map, and we have all the components of that are using in all the chips that are composed the PCD counter. So in total in this chip we have 20 registers and 46 logic elements. So in the chip planner we can see that components in blue that are here, and if we count all the cells that are in blue, we get all the registers and the logic elements of the circuit. So the next step is to test the circuit, and for that we create the counter mod BCD mod 15,000 test bench. When we apply an steam process with different values to test the circuit like we want. And in model sim, we now have this timing diagram that we have the clock, the clear direct, the count enable, the count, the outputs that count the to 15,000 and terminal counter 15. So after the clear direct, we see that all values are 0 because clear direct is 1, and it goes to the initial state that it's 0 in all the outputs. But when clear direct is 0 and containable is 1, the circuit starts counting in the units. And when the units goes to 9, after that the teens goes 1 and the units start again the count. So when the count enable value is 0, the value that are in this moment keeps from every clock that we want, and when count enable is 1, in the next clock starts count again. And if we go up counting, we can see that in one point of the counter, here at this point, when the counters arrives this value, um, this terminal counter goes 1, and after that the counter restarts again. So to do the functional simulation, it's like this, and for do the next step that it's the gate level simulation, we do the same but adding a VHO file with the cyclone 4, and we get this value for propagation time after the clock, that is 7.5 nanoseconds. So in Quartus Prime we can see the table that has the timing analyzer, but we need to start the timing analyzer, and after that go into timing analyzer. So in the report datasheet that is here, we go to clock outputs minimum time and get this value for calculate the frequency of the clock, that is 121 millions of operations per second. So that is the develop and testing the functionality of the circuit. And in conclusion, we get that the value of, or the functionality of the circuit, it's okay.